Java stage online again. Welcome, everybody. So I know that you have been wondering ever since this morning when this event started. You have been wondering and you have been wanting to know more about synchronous and asynchronous programming. Am I right? This is what we're about to experience in the next talk, where we have Lucian Roșu, who is a software engineer at ING Tech Romania and whose current look is a lot different than the one from his speaker picture profile, but we take change as a good omen in this stage. So we are looking forward to hearing the words that he has to say and also understand the deeper meaning that he wants to convey. He also told me before our talk, before his talk actually, that the key words for the following 25 minutes are lightweight concurrency. So with that, let's give a huge round of applause and welcome on stage in style, Lucian Roșu.
Thank you, Victor. Thank you a lot for the introduction. I will share my screen so we can get into the action as soon as possible. Now, just tell me if you can see my screen. Perfect.
All good.
So, a quick intro about myself. I am a software engineer, as Victor said, and in the last 4 years, I worked mainly in the JVM ecosystem, mostly with Java, Kotlin, or Scala, and I am passionate about distributed systems and high-performance computing. I work for ING Tech Romania, where I am involved in the development of some critical global systems that allows tens of millions of European customers to authenticate. Today, we will talk about an interesting project called Loom and its ambition to provide easy-to-use and lightweight concurrency on the JVM. Java is a null language, and it tries to be backwards compatible almost all the time. We have the gravitational pull of 26 years of existing code and patterns that might look impossible to escape. For today, I will start with some context, asking why do we need concurrency? What are the benefits of asynchronous programming over synchronous programming? And what dilemma we might develop? Then I'm going to talk about a possible solution for our dilemma that hopefully will be part of the standard library in the future. So my story for today is about threads. The JVM is thread-centric. Everything is built around threads. Exceptions provide useful information by placing the failing operation in the context of the current thread's call stack. So when we throw exceptions or we investigate stack traces, we do it on a specific thread. We also pass around data using thread lockers, for example, and we debug. We debug a lot, and each time we jump from one stack frame to another, we do it on a thread. Profiling is also thread-oriented. Providers organize work by threads when they show in the UI how much time is spent on processing or how much time is spent on waiting for IO synchronization. But in Java, a thread is represented by the only one java.lang.thread. And we have only one implementation, which is just a thin wrapper over a native operating system thread. That means the threads have a high footprint. Creating them requires allocating operating system resources, and scheduling them, assigning hardware to them is suboptimal, and we are bounded. A server can handle upward of 1 million concurrent open sockets, yet the operating system cannot efficiently handle more than a few thousands active non-idle threads. If we would imagine threads as part of the public infrastructure, they will not be taxis, but rather trains. Now, remembering about the gravitational pull of 26 years of existing code I was mentioning before, the thread.currentThread method and the thread lockers are omnipresent in libraries and frameworks. Just think for a second about the most popular logging libraries that we have. Almost all of them rely on the currentThread method when printing the thread name. Java is used, again, to write some of the biggest, most scalable applications in the world. Scalability is the ability of a program to gracefully handle growing workloads. One way in which Java programs scale is parallelism. We want to process a chunk of data that could grow quite large. So we describe its transformation as a pipeline of lambdas on a stream. And by setting it to parallel, we ask multiple processing cores to sink their teeth into the task. That mechanism was delivered in Java 8. But there is a different, harder, and more prevalent kind of scaling, which is about handling relatively independent tasks at the same time. That they must be served simultaneously is not an implementation choice, but a requirement. And we call that concurrency, and is the bread and butter of the contemporary software. Web services, sometimes highly loaded, having hundreds of thousands or millions of requests per second. Integration of external services, processing messages or events, all could be done in a concurrent manner. We aim to make good use of the available hardware that we have, and of course, we want to be able to scale and support the demand. Let's look over the programming models that govern Java and start with the synchronous programming. This model is idiomatic with the JVM platform, and because of the good support in the Java language, it is easy to read and develop synchronous code. There are conditional constructs, exceptions, thread lockers that can be used out of the box. We usually use the synchronous approach when we want to do things in parallel. And a good example is a web service. For each request, we can create a new thread that will handle the input and maybe produce an output. But creating threads might have performance impacts. A thread is a scarce resource, costly to create and limited in number. And it's limited because an operating system can deal with only a few thousand threads. What we do when the demand has a higher magnitude factor and we need to handle millions of requests. Horizontal scaling might be a solution, but we need to think also about the infrastructure costs. One more thing about synchronous programming is that I/O operations are pretty common and threads are consuming their time in a waiting state. Basically, we might waste operating system JVM resources while waiting I/O operations to complete, resources that can have a better use. In the previous slide, I said that threads are costly to create. A solution for this issue is the usage of the thread pools. We can create a bunch of threads upfront, and using a thread pool, we can later reuse them. But a thread pool is not a bulletproof solution. The cost of creating a new thread is so high that we reuse them happily, paying the price of leaking thread lockers or having a complex cancellation protocol. Another programming model that can be used in Java is asynchronous. The main gain of asynchronous over synchronous programming is the possibility to scale easier. But it has some drawbacks. It is not idiomatic with the language. Java offers you the proper tools for doing things in a sequential, imperative way using control constructs and exceptions. When you want to do things asynchronous, you might rely most of the time on callbacks. Callbacks are hard to read and use. Exception stack traces no longer provide a useful context. When single stepping in the debugger, we find ourselves in scheduler code, jumping from one task to another. Profiling an application under I/O load might show us idle thread pools because tasks waiting for I/O do not keep holding the thread by blocking it, and instead it returns to the thread pool. Nowadays, we have a lot of third-party libraries that help us dealing with asynchronous programming, but even with them, reasoning about the code base will give you the feeling that the way of doing things is unnatural, not related to the language. With those two programming models in mind, synchronous and asynchronous, we develop a dilemma. And we have to think if we want to have an asynchronous approach that will increase our throughput while not overwhelming the infrastructure costs, or keep the traditional synchronous models. Both choices have a considerable financial cost, either in hardware or in development and maintenance effort. And the developer experience matters. We want to have happy developers that write uncomplicated code, which is also performant. And here the Project Loom kicks in. Project Loom wants to provide to the developers the possibility to code in a synchronous fashion and scale like asynchronous under the hood. It lets you write programs in a familiar style using familiar APIs and in harmony with the platform and its tools. That's all in order to reach a balance of write time and runtime costs. As you can see from the code snippet, the java.lang.thread is still representing all the threads in code, at runtime, in the debugger, and in the profiler. No language changes are needed, and no new keywords are added into the language. A virtual thread is not a wrapper around an operating system thread, but it is a Java entity. Creating a virtual thread is cheap. We can have millions, and we don't need to pull them. Besides creation, blocking is also cheap. The context switch doesn't require a call to the kernel. We have the freedom of being synchronous without worrying too much about the performance. And we are Java idiomatic, and we use the same control structures, we rely on exceptions, and we are context aware. This helps a lot during the debugging sessions. In other languages, the idea of green threads is also present. We have fibers in Scala in different libraries like Cats Effect or Zio. We have coroutines in Kotlin, and we have Go routines in Go. But how Project Loom actually works? The traditional, well-known implementation of a thread is just a thin wrapper over an operating system thread. Hence the 101 mapping between a Java thread and an operating system native thread. But in Loom, things changed. Now we have an end-to-end relationship between a virtual thread and an operating system thread. Multiple virtual threads are multiplexed in fewer operating system threads, and between them stays a scheduler. The scheduler has the role of attaching a so-called carrier native thread to a virtual thread and is attached. The default scheduler that comes with Loom is based on a fork join pool with an work stealing algorithm. And there are no guarantees that once a virtual thread started on a native thread, after a certain suspension, it will continue on the same native thread. But there is freedom of change. We can plug in our custom scheduler and define the logic that fits our needs better. Let's visualize how virtual threads are working. Imagine a time frame. On this time frame, we will have 2 operating system threads, and we will spawn 3 virtual threads. At T0, the virtual thread number 1 will start. The scheduler will assign a native carrier thread to it, which will be the operating system thread number 1. A few moments later, virtual thread number 2 will start. The scheduler, again, will assign an operating system thread to it, which will be the operating system thread number 2. But at T1, something is happening. The virtual thread 1 decides to block. Maybe some IO operation is going on, and the scheduler will suspend it. And now the operating system thread 1 is free, no longer assigned. Shortly after this, our 3rd virtual thread decides to start. The scheduler will look for a free operating system thread, and it will assign the operating system thread number 1 to it. At this moment, there are no operating system threads left in the underlying thread pool, but if we pay attention to the slide, just before T2, the virtual thread 2 decides to finish its execution, and the scheduler will notice that, and it will disattach the operating system thread 2 from it. At T2, virtual thread 1 decides to continue. The IO operation has finished, and the virtual thread is ready to continue its execution. Now the scheduler will assign to it the operating system thread 2, a different thread comparing to the one that was used before. operating system thread 1, and the virtual thread will continue to execute and finish its work. The developer doesn't know the scheduling that is happening under the hood. The yielding and resumming happens deep in the JDK libraries. Virtual threads are preemptive, not cooperative. They do not have an explicit await operation at the scheduling. Rather, they are preempted when they block on I/O or synchronization. The virtual threads deserve a comparison with the operating system threads. There are 3 big differences between them. And let's start with the stack. The stack on the operating system threads is of fixed size, but modifiable on the virtual threads. You pay as you go, as you use. The metadata that the JVM needs for the operating system threads is around 2 kilobytes, comparing to a few hundreds of bytes on the virtual threads. And the context switch is way cheaper from a time cost perspective on the virtual threads. We can switch contexts and pay around 200 nanoseconds on the virtual threads, comparing to 1 up to 10 microseconds on the operating system threads. And this is happening because the virtual threads are concrete Java entities, where the operating system threads are just wrappers around the native threads. Now, how can we create threads from the code perspective? The classic way of passing a runnable to a thread and scheduling it for execution is still present. We can use the start virtual thread method to schedule for an execution a runnable on a virtual thread. This is very similar to what we have right now in the API for the operating system threads. Besides that, we have a kind of a builder available that we can use. The method of virtual can be called, and it has a bunch of other methods that are available for configuring things like allowing the usage of thread lockers or plugging in a new scheduler or defining names and so on. A second creational pattern besides the builder is the factory. The well-known thread factory will also support the creation of virtual threads. So you can create them on demand. And the factory can be used as a parameter for an executor service, for example. Besides creation, let's also look into the stack trace, because we said that we are context aware now. We don't lose the context anymore. A powerful thing about virtual thread is that they will help the developers to be context aware and not lose the trace. As you can see from my example, if I am creating a new virtual thread and I am dumping the stack, I have the whole chain of stepping points that I need in order to properly debug. The debugger agent that powers the Java debugger wire protocol and the Java debugger interface, the one that supports ordinary debugging operations like breakpoints, single stepping, variable inspection, and expression evaluation, works for virtual threads as it does for classical threads. And all of this is possible because under the cover, the VM has been updated to support a new construct of scoped stackful delimited continuations. Sometimes we need structured concurrency, and we need execution contexts that are bound to a specific block of code. The executors have been updated to support virtual threads. We don't have to pass a specific thread factory when we want an executor to use virtual threads. We can use the new virtual thread executor method directly. And in our example, on line number 7, when we invoke the tasks, the executor will create a new virtual thread for each callable, and it will schedule the tasks to be run in parallel. Then we can use the Stream API, for example, and handle our flow as much as declarative as we want. But the virtual threads are not a recipe for everything. There are use cases when blocking a virtual thread will also block the underlying operating system thread, and this will end up in service degradation, and the throughput of the application will be decreased. For example, if we have some native invocations through GNI, those will certainly block the operating system thread. Also, if we hit any synchronized block or method with our virtual thread, again, our operating system thread will be blocked. I know that there are high chances to hit a synchronized structure, and this could be a bottleneck, but there are some mitigations that I will present on the next slide. Meanwhile, the limitations of the synchronized will eventually go away, but we know something for sure. Blocking via GNI will remain. I was mentioning on the previous slide the synchronized structures. If we don't want to block the underlying carrier thread when hitting a synchronized block, we can use explicit locking mechanisms. And for example, if we have some IO operations that are under the umbrella of a synchronized block or method, we can use stamp lock, for example, and let the application efficiently enjoy the power of Project Loom. But as a first step against possible migration to Loom, it will be the identification of the places where the carrier thread, the native operating system thread, could be blocked and mitigate those situations. As a retrospective, the project started back to 2017, and right now it is in early stage access next to JDK 17. If you want to use it, you need to explicitly download the JDK 17 binaries that include also Project Loom. The binaries are available on the JDK website, and in the next slides, I will share the links. Beside the current state, the project has few more aspects that will put some effort into. Between the topics that are under the radar, we can mention channels, if we want to properly communicate between the virtual threads, interruption and cancellation, or scoped variables as an alternative to thread lockers. But as the next steps, unfortunately, we don't have a clear roadmap from Oracle, like having a timeline saying that in 2 years we will have a GA for the Project Loom. Everything will depend on how the things will evolve and on the feedback from the consumers that decide to play around. Some key takeaways for the Project Loom is that, and I think the most important key takeaway is that the java.lang.thread is still representing all the threads. That makes somehow the project work in a backwards compatible manner, and it will also give the freedom to the developers, or developers of libraries and frameworks to properly implement virtual threads or continue with the traditional operating system threads. Beside that, creating virtual threads is cheap, so we can have millions and we don't need to pull them. And blocking a virtual thread is also a cheap operation, so we can be synchronous. We want to be idiomatic with the platform. If you want to find out more about the Project Loom, you can access their official website by using the first link. The state of Loom is like a project manifest, and it describes in details all the things that Loom wants to provide to the consumers. Also, if you are interested in providing feedback or asking questions, you can use the mailing list, or you can just subscribe to it and follow the discussions that are happening for the project. Also on GitHub, you'll see a lot of activity, and because of that activity, I have the impression that the Project Loom will actually hit a GA in the future, and hopefully it will be implemented in the standard library. That was for today. Thank you for listening to me. I hope you enjoyed the presentation and got excited about what Project Loom has to offer. Now, Victor, tell me if there are questions in the chat, so I can gladly respond to them.
Indeed, we do have a couple of questions for you. The first one comes from Adrian, and he is wondering, how are thread lockers being handled when a virtual thread blocks and is then resumed by having a different OS thread attached?
Yeah, the thread lockers are mitigated by the continuations themselves. This is a new structure that is implemented in Loom, and you can imagine the thread lockers like a state machine. The continuations will have a state that on the resuming will keep all the state in that pay-as-you-go stack that I mentioned. So the stack is of growing and shrinking size, and this is where the thread lockers will be put in for the moment. In the future, the thread lockers are not so compatible with the idea of virtual threads, And we'll have scope variables that basically will be the next generation or the retrofit of the thread lockers.
And another one coming from Tudor, can this also be beneficial in API resource utilization? For example, like in lower cloud expenses?
Yeah, somehow it always depends on the scheduler. So the performance of your solution, or basically the cost usage, or the schedule, all the scheduling mechanism is done in the scheduler. By default, the scheduler that comes with Project Loom is optimized for transactions. And as I said, we have a for-join pool with a work stealing algorithm. But you have the freedom to change the scheduler and have one or develop one that maybe better suits your needs. Something else, Victor?
Yeah, and one last question, which is, I would say, a bit more general regarding your talk. What are some real-world scenarios where you use this? So becoming a bit more pragmatic.
Yeah. So it's pretty common in the JVM world, or at least between the Java developers, to create web services, right? And right now, the most famous framework, for example, Spring. And if you use Spring Web MVC, for example, and rely on the, let's say, blocking solution, you have a servlet implementation that will use a thread pool and reuse the threads for each request. But you have a cap, right? I said that we are bounded to the number of the threads that the operating system supports. And what we do if our infrastructure supports millions of requests, but we are bounded by the operating system that only supports 2,000 or 3,000 of native threads at a time. So this layer of abstractization will be, I think that was the idea in mind, to be provided to the web services, where you can handle a lot of open sockets on the operating system, but you still have the drawback of the native threads that are a scalability bottleneck. And also it is used for the scenarios where we have a lot of IO, right? For example, we have a web service that depends also on other services, and for each other service, it will have some IO in between, right? Requesting another microservice, another node, and waiting for the result. While waiting for the result, the thread might be blocked, and we waste resources. We can mitigate, for example, that with completable future and go asynchronous and enjoy all the new APIs that were introduced in Java 8. But we still, in the end, will run our execution on a thread that can be blocked. And in Loom, because of the continuations and the smart scheduling and the idea of having the threads as Java entities, it will be cheaper for us to have context switch and to scale.
Excellent, Lucian. Thank you so much for all these details and for answering the participants' questions. Just so you know, reactions are going crazy. So you did get a big round of applause right here at the end. So congratulations and thank you so much for your talk.
Yeah. I will also be available in the lobby. So if anyone wants to have an one-on-one chat with me and discuss more about Project Loom, I will be available there. And yeah, thank you again for having me there, and enjoy the next sessions.
Thank you, Lucian. And indeed, I also wanted to build on Lucian's point and invite you to the expo area, where you can also find the ING booth. It's on the first floor. It's in the right part of your map. So please feel free to go take a look and explore what they have there. This being said, I cannot express how excited I am, so therefore you should also be by our next speaker. I won't say who he is because you have the agenda on your screens probably, and I will introduce him to you in 5 minutes after this short break. So feel free to network, explore the expo area, check out the other stages, and come back here at 4 o'clock on the dot. See you then.